Hello, everyone, and welcome to the last lecture slide. Whatever it's called. Welcome to the last lecture of the semester, calculus with parametric equations. So we're going to look at how do we calculate slopes of tangent lines, areas, things like that when we're working with parametric equations instead of just a single function of a single variable. So very fun stuff. So announcements, again, everything that you need to do in this class is in MyOpenMath. All assignments are available to you, every project, every quiz. So make sure you're working on all of that. The last day, today is the last day of new material, like I said. So next week, you can still come to class on days when someone will be available. I will make an announcement when that is. But you will be able to come in and attempt quizzes, work on projects, ask questions about quizzes and projects, and all that. So feel free to come in those mornings and work on what you need to do. Also, feel free to come in even on days when someone won't be there. Feel free to come in and use that quiet classroom to work on project stuff. Okay. And then announcement number 3, there is no final exam, quote unquote, in this course. We have a final exam time scheduled for May 21st at 8 a.m. to 10:30 a.m. In our usual classroom. So what that time will be used for, if you've already gotten the grade that you want, if you only want a B and you've gotten a B, then leave campus early, or at least you don't need to show up to my final exam period. If you want an A, but you haven't gotten an A yet in terms of assignments completed, then you can come into that final exam and you can attempt any quizzes that you still need to get through, or you can just come in and finish any projects or homework or whatever that you need to finish up to get the grade that you want. 10:30 a.m. on May 21st is the ultimate deadline for everything in this class. Okay, I will not accept anything after 10:30 a.m. on May 21st. Okay, so whatever you're done with at that time on May 21st, that's what you get. Check off whatever you want in the syllabus. You can see what grade you have. You do not have to wait on me to tell you what grade you have, right? So make sure to come in to that exam period. Again, there's no final exam, but come into that exam period if you want to come in and take any last attempts at any sort of quizzes or projects or anything like that. All right, so those are the announcements. Let's dive into these last set of slides. So first we're going to talk about, let's say I have a parametric curve defined by the equations y equals y of t and x equals x of t. And in Calc 1, one of the first things we wanted to do with limits and derivatives is find the slope of a tangent line. And in fact, that was sort of the motivation for the idea of the derivative, both in a Calc 1 class, and from a historical perspective as well. So let's look at how we can calculate the slope of the tangent line if we have some curve defined by parametric equations y equals y of t, x equals x of t. Okay, so let's say I want to find the tangent line, this slope of the tangent line at this point here that corresponds to x of t naught, y of t naught. Okay, so here's my x-axis, here's my y-axis. And notice what I've drawn here is clearly not the graph of a function, right? And that's, again, kind of the power of parametric equations, is we can graph things, we can describe things that aren't really defined in terms of functions of a single variable, things that, kind of wrap around on themselves like this or something like that in a pretty straightforward way. So I want to find the slope of the tangent line, which we'll still denote with dy dx. The slope of the tangent line, if this is my tangent line, y equals mx. Well, let me use y naught plus m times x minus x naught. The slope of the tangent line is still defined as like change in y over change in x, right? So what we're going to do, this y naught is like y of t naught, and x naught is x of t naught. Well, we know a point on this line. The only other thing we need to do is figure out the slope of the tangent line there. And what we're going to do is exactly what we did in Calc 1. We're going to take limits. So I'm going to, instead of trying to figure out that slope there, I'm going to draw, put in another point right here, which I'll call x of t1, y of t1, where t1 is really, really close to t naught, right? And what I'm going to do is I'm going to find the slope of the secant line through those 2 points. So there's my secant line. And the slope of the secant line is really, really close to the slope of the tangent line. And in fact, when I take the limit as t1 approaches t naught, then I in the limit will get the slope of the tangent line as long as this curve is well behaved, right? So let's look at what happens there. What is the slope of that tangent line? So I'll call this, of the secant line, I'll call it m sub secant line. Well, slopes of lines, it's still defined as change in y over change in x. So that's y of t1 minus y of t naught over x in t1 minus x of t naught, right? The change in x from the big red point to the small red point, the change in x is, well, x of t1 minus x of t naught. And the change in y is y of t1 minus y of t naught. Okay, so there's the slope of the secant line, and so we'll get the slope of the tangent line, m tan, by taking the limit as t1 approaches t naught of this difference quotient, y of t1 minus y of t naught over x of t1 minus x of t naught. Okay. And assuming, so as a reminder, with limits, I don't actually care about what happens when t1 equals t naught. I only care what happens when t1 is close to t naught. So I am safe to multiply and divide by t1 minus t naught. So this is the limit as t1 approaches t naught of y of t1 minus y of t naught over t1 minus t naught. So I divided by t1 minus t naught, and so I can also multiply by that. Let me scooch this over a tiny bit. Times t1 minus t naught over x of t1 minus x of t naught. Cool. And so what is this equal to? This is equal to the limit as t1 approaches t naught of y of t1 minus y of t naught over t1 minus t naught over x of t1 minus x of t naught divided by t1 minus t naught, right? And now when I take the limit as t1 approaches t naught, you should have really at this point right here, I hope that you recognized that, hey, that's like the difference quotient. That right there feels like y prime of t, y prime of t naught. You should have at least recognized that one, I would hope. But if you didn't, that's okay. So as t1 approaches t naught, the top looks like y prime of t naught. So that's a derivative with respect to t. That's because y is a function of t. Okay, divided by x prime of t naught. There we go. There's the slope of the tangent line at the parameter value t naught. And so, knowing that x of t naught, y of t naught is the point on the tangent line, we can actually say that the equation of the tangent line, so the equation of tangent line is y equals y of t naught, whatever that is, plus y prime of t naught over x prime of t naught times x minus x of t naught. Wow. How cool is that? Now notice, I am assuming one thing here. Can you guess what it is? Can you see what it is? One thing that I'm assuming is that x of t1 minus x of t naught is not constantly 0, right? And if I have a curve that is sort of vertical, then the slope of the tangent line is undefined. So that is an issue there to keep in mind. Okay. But otherwise, this is how we define the slope of the tangent line. All right, so let's look at an example. Let's find the equation of the tangent line to the parametric curve defined by cosine of t, cosine cubed t, sine cubed t when t is equal to 2 pi over 3. This curve is called the asteroid, and if we look at that curve, we get cosine of t to the third in Desmos, sine t to the third for 0 less than t less than 2 pi over, just 2 pi to begin. So here's what that curve looks like, the asteroid curve. I actually don't know why it's called the asteroid curve. Doesn't really look like an asteroid to me. But here is the point that we're interested in. Cosine of 2 pi over 3 cubed, comma, sine of 2 pi over 3 cubed. Okay. So we want to find the slope of the tangent line at this point here, minus 1/8, comma, 0.64952. Okay. So that's where we want to find the slope of the tangent line. All right. So in order to do that, I need to know what is x of t. Well, x of t is the x coordinate here, which is cosine cubed t. And what is y of t? Well, sine cubed t. Okay. So to find the slope of the tangent line at any point, we do dy dx is equal to y prime of t. So this is at some t value over x prime of t. So in particular, dy dx at t equals 2 pi over 3 is going to be y prime of 2 pi over 3 over x prime of 2 pi over 3. Okay, so now I just need to find y prime and x prime using Calc 1 rules, derivative rules, right? So y prime of t using the chain rule, I get 3 sine squared t times cosine of t. X prime of t, again by the chain rule, is going to give me 3 cosine squared t times negative sine of t. Amazing. So finding dy dx, that gives me well, y prime of t. So for any t, that gives me 3 sine squared t cosine of t over 3 cosine squared t times minus sine of t. So we get 1 cosine cancels there, 1 sine of t cancels there, and these 3's cancel. And so I'm left with just negative tangent of t in the end. So that means dy dx when t equals 2 pi over 3 is negative tangent of 2 pi over 3. So sine of 2 pi over 3, that's what? Square root of 3 over 2. So this is negative square root of 3 over 2 over cosine of 2 pi over 3. That's minus 1/2. And so we get some cancellation, negative y's, and also the 1/2's cancel, and I'm just left with square root of 3 there. So the slope of the tangent line is square root of 3. And the point on the line here, x of 3 pi over 2, is cosine cubed of 3 pi over 2. So again, that's 1/2, minus 1/2 rather, to the third, which is minus 1/8. And y of 3 pi over 2 is, that's that square root of 3 over 2 cubed, which is, 3 square root of 3 over 8. And so we get the equation of the tangent line. Y equals, if you want, you can use point slope form, right? Y minus 3 square root of 3 over 8 equals square root of 3 times x plus 1/8. And if you want to move that 3 square root of 3 over 8 over to the right, you can. But let's verify that this is correct by plotting this tangent line. Y minus 3 square root of 3 over 8 equals square root of 3 times x plus 1 over 8. And there we go. We get our tangent line. Perfect. If I zoom in, again, tangent line and the actual curve are indistinguishable. Amazing. All right. My computer is being very slow right now. Okay, so let's see how I can find a second derivative. Before I do that, so a second derivative with respect of y with respect to x for curves defined parametrically. Before I do that, let's notice one thing, that the derivative of y with respect to x, that's the derivative with respect to x of y, and that led to y prime of t, so the inside function here, the inside function with a derivative with respect to t divided by x prime of t, the variable we're taking a derivative with respect to, a derivative with respect to t there. Okay, so if I'm taking the second derivative of y with respect to x, I don't need to go through the whole limit process again, because this is the same thing as the derivative with respect to x of dy dx. But dy dx is a single function of t, right? Y prime of t over x prime of t. So we need the derivative with respect to x of y prime of t over x prime of t. But now just do what we did here. Okay, the derivative with respect to x of a function is the derivative of the original function with respect to t over the derivative of the function we have in the that we're taking the derivative with respect to. That function we're taking a derivative in the denominator now with respect to x. Okay, so now I'm going to treat this whole thing like y. I'm going to take the derivative of this with respect to t. That's going to be the top. Okay, so the derivative of y prime of t over x prime of t with respect to t gives me, well, I need to use the quotient rule, right? Low d high, so x prime of t times y double prime of t minus high d low, y prime of t x double prime of t over the square of what's below, x prime of t squared. So there's the derivative of the inside function. This is kind of like a parametric version of the chain rule, but not exactly. So there's the derivative of y prime over x prime with respect to t, and then I'm going to take that and I'm going to divide it by x prime of t. Which leaves me with x prime of t, y double prime of t, minus y prime of t, x double prime of t, over x prime of t cubed. Amazing. So let's use this to find the second derivative of an easier function. We're not going to use the asteroid. Let's just go with the circle. Okay, so suppose x of t equals cosine of t and y of t equals sine of t. Okay, find the second derivative of y with respect to x at x, or sorry, when t is, let's go pi over 4. Okay. This, by the way, holds, we're going to say this is for 0 less than or equal to t less than or equal to 2 pi. Okay. So that's what we want to do here. So the second derivative of y with respect to x when t is pi over 4. So this is just going to give us, well, up here we've got our formula. This is x prime of t, y double prime of t, minus y prime of t, x double prime of t, divided by x prime of t to the third, evaluated at t equals pi over 4. Okay, so I plug in what x prime, y double prime, what all these things are. So if x is cosine of t, then x prime of t is negative sine of t. So we get negative sine of t there. And y is sine of t, so y prime of t is cosine of t, and y double prime of t is negative sine of t as well. Okay, so there's that derivative. Minus y prime of t, well, y is sine of t, so y prime of t is cosine of t. X double prime of t, so x prime is minus sine, and therefore x double prime is minus cosine of t. And I'll divide by x prime of t, which is minus sine of t to the third. Okay. And we're going to evaluate this at t equals pi over 4. Now, in the numerator, notice that we get a lot of simplification because this is sine squared t plus cosine squared t, and then over minus sine cubed t. The numerator, this is still evaluated at t equals pi over 4. The numerator is just 1, right? So this is negative 1 over sine cubed t, and then evaluate at t equals pi over 4. So let's plug in that t equals pi over 4 and see what we get. We get dy dx at t equals pi over 4 equals, well, negative 1 over sine of pi over 4 is square root of 2 over 2. So square root of 2 over 2, and then we'll square it. Or sorry, no, we'll cube it. Sorry. Which leaves me with negative 1 over, well, square root of 2 cubed, that's 2 root 2. And 2 cubed is 8, so that's like that. And simplifying a little bit, this is negative 4 over the square root of 2. And if you're someone who hates square roots in the denominator, feel free to multiply top and bottom by the square root of 2, which leaves me with negative 4 square root of 2 over 2 times 2, sorry, square root of 2 times square root of 2 is 2. Bingo, bango. That leaves me with negative 2 square root of 2. Gross. But we got it. It's correct. Now, how could we check this for ourselves? Well, again, we're looking at a circle here, a circle of radius 1. So the function that defines that, f of x, if I change to functions, this is the square root of 1 minus x squared. And the point that we're interested in, x equals, or sorry, t equals pi over 4, that point on the unit circle is square root of 2 over 2, comma, square root of 2 over 2. Okay. So there's the point that we're looking at. So really, phrasing this question not in terms of parametric equations, this is like asking what's f double prime of square root of 2 over 2 here. So here's f prime of x, that thing, and then here's f double prime of x, that thing. So f double prime of square root of 2 over 2 gives me negative 2.828. And we got negative 2 times the square root of 2. We got the exact same thing. Okay. And, with functions, directly, you could do this, but you need to use, frankly, some grosser chain rules than what we used for this. So parametric equations sometimes are more natural to use to work with things like derivatives, and it helps you avoid some potentially gross chain rule problems. All right, so there's one more thing that we tend to do in calculus with curves, and that's fine. So we found tangent lines, we found second derivatives, which tells me about concavity, right? The other thing that we tend to do with curves in calculus is find areas beneath them, right? Underneath the area between a curve and the x-axis. So let's see how we can do that, and the answer is we do it exactly the way we did before. Here's x, here's y, and I'm going to assume that my curve is a little nicer than the one I drew above, just because it makes the derivation a little prettier or a little less tedious. But you could do this with something that sort of loops over itself. Technically, but that's a little gross. So we'll assume that x prime is never negative, okay? Or x prime is actually never 0. So let's say we have this curve defined parametrically by x of t, y of t. That's what this curve looks like. Okay, and we're going to do, again, exactly what we did before. We're going to break this, we're going to break the t interval up, and this, again, we'll say is true for t between a and b. Okay, so we're going to break this curve, the t interval up from a to b, into n equal parts, right? So this will be like this will correspond to t equals a. Here's t equals a plus delta t. Here's t equals a plus 2 delta t. Here's t equals a plus 3 delta t, and so on and so on and so on. Where delta t is going to be b minus a over, we're going to use n sub-intervals, okay? And here, let's get to a general, t equals... we'll call this ti equals t naught plus I delta t. And by the way, this would be like t naught, this would be like t1, this would be like t2, this would be like t3, and so on. So there's ti equals t naught plus I delta t, and here's t I plus 1, which equals t naught plus I plus 1 times delta t. Okay. Now, we are trying to find the area underneath this curve. So I'm still going to draw in rectangles corresponding to these points along the curve. However, I'd like to point out that just because the t values are spread out equally, that doesn't mean my x values are necessarily spread out equally, right? So I might get a bunch of unevenly spaced rectangles here. So let's say we're using right-hand Riemann sums. Okay. So we get here and we're looking like we're looking at a rectangle like this. Okay, and at this point we need to ask ourselves, if I call this x naught and this x1, x naught is x of t naught, x1 is x of t1. This is x2, which is x of t2. This is x3, which is x of t3. This looks like xi, which is x of ti, and this is xi plus 1, which looks like x of ti plus 1. Okay. What we're going to do is we're going to look at the area of this arbitrary rectangle. Now, areas of rectangles are still just width times height. So the area of this arbitrary rectangle, I'll call it AI, is, well, width is xi plus 1 minus xi times height. Well, that's going to be we're using a right-hand Riemann sum here. So y of ti plus 1. Okay. Easy squeezy. All right. And so when we're looking at Riemann sums here, I'm going to add up a bunch of stuff that looks like that. So I'm going to get A, the approximate area under this curve, is going to be the sum I equals 0 to what? 0 to n minus 1, technically, of, I'm going to write it as y of ti plus 1 times, and then we're at xi plus 1 minus xi. And that's not quite the form of a Riemann sum. I can't just now say take a limit as n goes to infinity and then I just get the integral of y dx, because that's not what we get. I need some sort of like delta t. I need some sort of constant delta t. That's what we got with Riemann sums. And so what I'm going to do is I'm just going to put it in there. I'm going to say this is a sum I equals 0 to n minus 1 of y of ti plus 1 times xi plus 1 minus xi. I'm going to divide this by delta t and multiply by delta t. Okay. xi plus 1 and xi, by the way, what those both are x of ti plus 1 minus x of ti. Easy squeezy. All right, so now let's recall the mean value theorem for derivatives, because this thing should scream to you, hey, that looks kind of like a derivative. If delta t gets really small, then that's going to look like x prime of ti, right? Or ti plus 1, actually. And by the mean value theorem, we can actually say that there's some ti star between ti and ti plus 1, such that this is equal to x prime of ti star for some ti star between ti and ti plus 1. Okay? So that's by the mean value theorem. By mean value theorem. So this is really equal to the sum I equals 0 to n minus 1 of y of ti plus 1 times x prime of ti star times delta t. And now at this point I say, oh, well, instead of using right-hand Riemann sums, I didn't really have to use right-hand Riemann sums. Why don't I just come back up here and say, instead of using ti plus 1, let's use that ti star that we're getting somewhere in between those two. It doesn't have to be right in the middle like I've drawn it. Maybe ti star is like right here. Who knows? But for each ti, we're getting something a little bit different. So maybe here the rectangle goes up to that ti star. Okay. And I go back and I make that change and pretend like I knew it all along, which happens quite a bit in mathematics. Okay. So instead of using ti plus 1, I'm going to use ti star. That's coming from that mean value theorem. And in fact, again, I can come up here and if I wanted to, you could make that change here to say that that looks like x prime of ti star times y of ti star. Okay. And now that I've made that change, this does look exactly like a Riemann sum. I'm going to say A equals, technically this should be approximately equals here. The area under the curve between t equals A and t equals B is equal to the limit as n goes to infinity of that sum. X prime of ti star times delta t, which is then equal to, once I take the limit, this is equal to the limit from So it's now this is delta t. This is depending on t, how t is changing. So t is going from a to b, and then y of t times x prime of t dt. Okay. Another way that you can sort of see this without going through the Riemann sums that you might like a little bit better is you can say, if I can view this as y is a function of x, if I can eliminate the parameter here and say this is going from x of a to x of b, then the area here I could also find as the integral from x of a to x of b of y of x dx. But then I can basically do a u substitution. X equals x of t, which means dx dt is x prime of t, so that dx is x prime of t dt. So when x is x of a, what is t? Well, t is just a. When x is x of b, what is t? Well, t is just b. And then y of x looks like, well, y of x of t, right? So I'll just call that y of t. And then dx looks like x prime of t dt. So this is another way that you can kind of work this formula out for yourself, maybe without resorting to Riemann sums. It's a little less formal, less rigorous, but it gives you the same results. Okay, but either way, this tells you the area under a parametric curve, between a parametric curve and the x-axis, between t equals a and t equals b. Okay, so let's finish this off by finding the area in the first quadrant bounded by the parametric curve cosine cubed t, sine cubed t. This is, again, true for 0 less than or equal to t less than or equal to 2 pi. We will need to adjust. We'll need to figure out the bounds here in a second. But let's do this. Okay, so I'm going to do an integral of y of t times x prime of t dt. And I just need to figure out what are the bounds on that integral. So let's go look at this parametric curve. Get rid of all this junk. Bye. We're looking at cosine of t cubed, sine of t cubed. Okay. And this is for 0 less than t less than or equal to t less than or equal to 2 pi. But no, so that gives us our full curve. But I only want to know what part of this curve is in the first quadrant. So apparently it's 0 less than or equal to t less than or equal to, well, if I go pi, that goes too far. It's like 2 times too far, right? So apparently I want to go to pi over 2. There we go. So the t bounds of 0 to pi over 2, that's what we want to use here. Okay, so let's use that in our integral, the integral from 0 to pi over 2. And now let's evaluate this integral. This is the integral from 0 to pi over 2. Y of t is sine cubed t. X prime of t is 3 cosine squared t times negative sine of t dt. And this gives me the integral from 0 to pi over 2 of negative 3 times sine to the 4th t cosine squared t dt. And technically, this is one of those that you can use cosine of 2t is cosine squared t minus sine squared t, which means that cosine of 2t is either 2 cosine squared t minus 1. So I can solve for cosine squared t if I want to. Or I could solve, come on, get back here. Or I could solve for sine squared t. 1 minus 2 sine squared t if I wanted to, but it's late. I don't want to do that. Let's just let Desmos do this integral for us. Okay, so Desmos does this integral for us. We get minus 3 times the integral from 0 to pi over 2 of sine of t to the 4th times cosine of t squared dt, and we get minus 0.294524, blah, 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 blah. Take a second and think why this answer is negative, other than it spit out a negative 3. Think a second about why this answer is negative. If you said it's because this curve gets traced out from right to left instead of from left to right, that's the correct intuition here. Okay, so if I want to know the true area under here, you can take, in viewing this as a geometric shape, you can take the absolute values. That would be fine. Okay, if we want to view this in terms of, again, a function of x and doing what we did earlier in the semester, one thing I could do is I could say that this function, or this curve, can be defined as x to the 2/3 plus y to the 2/3 equals 1. There's this function. And so if I want a function of x, well, then apparently f of x equals 1 minus x to the 2/3 all to the 3/2 should do it. And so I could also just integrate from 0 to 1 f of x dx, and notice we get the absolute value of what we got up here. So one thing to keep in mind when you do these integrals with parametric curves, you do want to keep in mind that if the curve gets traced out from right to left instead of left to right, then the answer you get might be counterintuitive to what you expect. So keep that in mind, because we live in a right-handed world and read left to right. Okay. So there we go. So that's how you find areas of parametric curves, and that's how we're going to end the semester. So thank you all for a great semester. If you have any questions, feel free to email me. Send me an email asking about any aspect of the course, grading, projects, quizzes, anything about that. And I'll try and get back to you as soon as I can. As a reminder, you should be able to go into class at least twice a week to work with someone, be it Sinclair or Dr. Walker or Dr. Hassinian. Someone will be there at least a couple days a week for you to take quizzes and ask questions in our normal class time. Okay, I will also provide you with office hours of people who you can go to ask questions and take quizzes as well. Okay, that's that. Thank you again so much for a good semester. Good luck with all of your other finals. Good luck with the rest of your work in this class. And I hope to see some of you next year. And to anyone who's graduating, congratulations. And I hope you have a fantastic career once you leave SU. Thank you, everybody.